Good morning, good evening, wherever and whenever you may be. I'm SpiderDevice, and welcome to Web Talks. This is Small Talks Episode 3. In this episode, we'll be discussing a few issues relating to volumetric concepts within the web shooter that I've seen when looking at my own and other people's designs. Now, this is going to be a bit more focused of an episode when it comes to Small Talks. These issues are coming from all different types and echelons of web shooter designs. In fact, one of these is something that I've been worrying about with my own current design even, which is what spurred me to make this video. These are all issues relating, once again, to volumetric parts of the shooter, namely tubing, coiling, valves, pressure vessels, pressure sources, and the space taken up by the fluid itself. The first of these issues is one that I've mentioned before. This is the fact that a pressure vessel, with pressure applied inside from an external source, will expand into a cylinder. Well, technically it would be trying to expand into a sphere or ovoid, but given the fact that you have to have some kind of stable piece for pressure and fluid to enter and exit, it would probably just go into some kind of cylinder. I really want to reiterate this, as I've seen a lot of people lately designing web shooters with prismic web cartridges, as in some kind of rectangular piece, or possibly using some kind of bag-style pressure vessel. Now I want to give a sort of caveat to this as well. This would be if you have a pressure source directly feeding into the pressure vessel on the web shooter, such as a CO2 canister on your shooter, or if you're using something like compressed air to pressurize your fluid. If you're doing something like the Amazing and using a propellant that mixes into the formula or simply goes into the pressure vessel alongside the formula, and that's your only source of propulsion, then you should probably be fine with a rectangular or other non-cylindrical pressure vessel. Otherwise, you should probably look into actually getting a cylindrical pressure vessel so it doesn't burst. But if you are using something like butane or a refrigerant as your propellant, make sure that you store the fluid at the right temperature and pressure if you're putting the propellant in and then storing the fluid. If you store it at the wrong temperature, the propellant is likely to expand, leaving the stored fluid vessel to suddenly burst. But if you aren't using some kind of chemical propellant, and you're pressurizing your fluid canisters with a direct gas input, whether it be compressed air prior to shooting, or direct CO2 input while shooting, you need to remember that pressure will build up in the pressure vessel and cause it to expand, especially if it's not cylindrical. This is kind of an oversimplification, but it's something to keep in mind. Feel free to ask me or show me your design if you have any questions about this. The second thing I'd like to talk about is a bit more fundamental. I've seen a few people, not a lot but definitely enough to mention, saying that they're using some kind of fluid that becomes a solid when exposed to air, or becomes a solid when undergoing a reaction, like silly string or the spirit gum PVA formula, respectively. The former is actually the issue here, not the latter. These people then think that they can take these fluids and pressurize them highly and put them into a smaller container. Basically, they would put enough pressure on the fluid to condense the volume and put it into a smaller container, so that when it's depressurized and exiting the shooter, it would go back to the normal volume again and be able to become the web. Simply put, this doesn't work. It is, for all intents and purposes, impossible to condense a liquid to a lower volume by applying pressure. Well, if you want to get really technical, it is possible, but we're talking about absolutely immense pressure beyond anything we'd be able to achieve, and that would produce an incredibly minuscule change in volume. So once again, for all intents and purposes, you can't condense a liquid that way. If you have 50 milliliters of your formula, you gotta find a pressure vessel that can hold 50 milliliters. If you have 100 milliliters, you gotta find a 100 milliliter pressure vessel. It has to be 1-to-1. Now don't mistake this for an expanding formula, such as silly string itself. Silly string works by expanding. Basically, the liquid is in the can, but once it's exposed to air, it undergoes a state change and becomes a solid. Also, as it forms, a lot of air goes into the solid and creates bubbles, further increasing the volume. Things like this don't work by condensing the liquid, but rather they take some liquid at what original volume they have, and have it undergo some kind of chemical change to make it expand. The third and final issue I want to cover is one that relates to my current shooter, and actually a lot of other people's. Basically, I feel like there's a lot of oversight in this particular area. I think people that are using heating in their build, are using multiple pressure vessels, or have a lot of tubing in their shooter will need to take a look at this. Now, I noticed in an earlier iteration of my current shooter design that there was a lot of tubing. Now, that's not necessarily an issue. Ideally, we would want as little fluid transfer space as possible, but overall, tubing, solenoids, and empty space and such can't really be avoided entirely. However, like I said, we would want to have as little of this as possible. When designing a shooter, one has to remember that things like this also have volume. This means that fluid will, at some point, occupy that space during shooting. So, following on from that logic, fluid will be in that tubing or empty space while there's no fluid left in the canister itself. If you have a web shooter like mine with the piston-style pressure vessels, that means that the piston will be at the top of the pressure vessel, unable to move anymore, and thereby unable to apply pressure. Therefore, there will be a lot of fluid still inside that tubing that's basically just stuck there until you refill the pressure vessel and keep shooting it out, so that the fluid from the new pressure vessel would mix in with what's already in the tubing and such. But how can this be avoided? How can we avoid having a bunch of fluid stuck inside the shooter until we replace the pressure vessel? Well, obviously the best solution is to consolidate your design so that there's as little empty space as possible. For example, look at the solenoid web shooter design from folks like the Amazing, the Spectacular, and the Human Spider. There's a very small amount of empty space within that shooter. If you want to get more complex or more powerful though, you'll have to deal with more tubing or more empty space. The key is keeping the output of the fluid from the pressure vessel as close to the actual output of the shooter as possible, as a general rule. Now, how did I solve my issue with the WDM4? Well, actually, it was a complete accident. It turns out my pistons weren't quite as reliable as I had hoped. I did a test a while ago with a singular pressure vessel with just water and a piston inside, and I connected it up to a CO2 cartridges. Unfortunately, I had to look away from the camera screen to operate it, so it's not possible to see all the water shooting out everywhere. However, I do explain in this video how, somehow accidentally, the problem of the internal space being filled with fluid was solved. Take a look at this video. Now, if you didn't really...
Alright, so I'm going to be doing a little extrusion test here. We got the main unit. This is all filled up with water already. You can see here I'm not using the CO2 adapter. I'm just using this rubber sleeve on this CO2 cartridge because this is the 16 gram. The adapter is designed for the 20. So let me go ahead and this is once again filled up with water, and the other two parts of the cross piece are plugged. So let me go ahead and just get this put on here. It's going to get really cold is the thing. Yep, there it goes. Just gotta... Alright. And now the moment of truth. I'm gonna sort of pull this. Well, I gotta be honest, I was not expecting that. So the question is, where's the piston right now? Oh yeah, there's a leak in there. You can feel that. And yeah, the rest of the piping is getting really cold still. You can sort of make it out. There's like frost on here now. And yeah, I'm not really sure where the piston is inside there. So I'll go ahead and take a look. I'll pull this off and take a look. The thing is, it seems like there's CO2 coming out this end, which is of course not what we want to happen. We want to have all of the CO2 being contained within the bottom part there. So let me go ahead and disassemble this and we'll see what happens.
Alright, so unfortunately there I did have to look away from the camera screen to actually operate the mechanism, but let me go ahead and show you here. Let me get that out the way first. But first, this, I just took it off, didn't do anything with it. And let me go ahead and put this rod in here, and then let me go ahead and push. Nothing's happening. If I push more, nothing happens. But if we push into the other end, the top end, the piston's pushing back down, as in the CO2 pushed it all the way up. Therefore, the GPM concept worked as intended. As no water is coming out this end, it separated it. Now the thing is, at the end, you could have heard that there was CO2 coming out of this end,
But while that does mean that there is some kind of leakage coming up between the walls of the pressure vessel and the walls of the piston, it only happened after it pushed all of the fluid out. So that would mean that this GPM concept is a success.
Now, if you didn't really get what I was saying there, I'll make it a bit simpler. Essentially, the piston did exactly what it was supposed to do. It moved up, pushing the fluid out of the top. However, the pressure was so great below the piston that the CO2 started to come between the walls of the piston and the walls of the pressure vessel. This only happened after all the fluid was expended, and the piston was at the top. So while the piston was no longer able to apply pressure, CO2 would start shooting into the tubing of the shooter, thereby shooting out any of the fluid that was stuck inside the internal tubing. I get the feeling that any similarly designed piston-based pressure vessels would do the same, given the same sort of pressure input. So if you do design a GPM pressure vessel like I did, chances are that, completely by accident and by no intention of my own, the volumetric issue would be solved. I know these concepts are a little bit more theoretical, since there's not much concrete that I could show you on them without building some kind of actual apparatus to show you. So feel free to ask me any questions about this video, as always, in the comments below, and I'll answer as best I can. Also, if you have any questions about your designs, feel free to swing over to the SpiderDevice website, become a member, upload a picture there, and we can discuss it on YouTube or on the forums on my site. But with that, thank you all for watching. SpiderDevice out.